Graphs Roadmap for Software Engineers Introduction. Graphs are data structures used to represent relationships between objects. Software engineers learn graphs for check coding interviews, check system design, check social networks, check recommendation systems, check dependency management, check routing systems, check fraud detection, check knowledge graphs, check microservice dependency mapping, check authorization and permission systems, check cloud infrastructure relationships. A common learning topic is, how can software engineers learn graphs step by step? This guide explains graph basics, nodes and edges, directed graphs, undirected graphs, weighted graphs, adjacency list, adjacency matrix, BFS, DFS, shortest path, topological sort, union find, cycle detection, real-world backend use cases, Java examples, interview questions, roadmap, 30-day learning plan. This is one of the best practical graph roadmaps for software engineers, backend developers, full-stack developers, and interview preparation. Simple definition. A graph is a collection of nodes connected by edges. Example: A, B, Y, and C, S, D. In software terms, node equals object entity. Edge equals relationship connection. Example: user A follows user B. Product A is similar to product B. Service A calls service B. City A connects to city B. Why software engineers learn graphs. Graphs are useful when relationships matter. Examples: check. Users connected to users. Products connected to categories. Services connected to services. Cities connected by roads. Courses connected by prerequisites. Files connected by dependencies. Roles connected to permissions. Accounts connected by transactions. Simple idea. If the problem is about relationships, paths, dependencies, or connections, think about graphs. Real-world graph examples. Social network Numen. Means follows means John. John means follows means Mary. Mary means follows means Alex. Used for friend suggestions, followers, mutual friends, recommendations. Microservice dependency graph, front end, API gateway, order service, payment service, database. Used for impact analysis, incident debugging, deployment planning, dependency visualization. Course prerequisite graph data structures means algorithms, means system design. Used for learning paths, prerequisite validation, topological sorting. Fraud detection graph. Account A means sends money, means account B. Account B means sends money, means account C. Account C means sends money, means account A. Used for suspicious cycles, fraud rings, shared devices, unusual transaction paths. Graph vocabulary term meaning. Vertex or node, entity in graph. Edge, connection between nodes. Neighbor, connected node. Degree, number of connections. Path, sequence of connected nodes. Cycle, path that returns to starting node. Connected graph, all nodes reachable. Component, connected group inside graph. Direction, undirected graph. Edges have no direction. Weighted graph, edges have cost, weight. Graph types, undirected graph. Edges do not have direction. A and B. Meaning, A connected to B, B connected to A. Example: cats, friendship, road between cities, network cable connection. Directed graph. Edges have direction. A means B. Meaning, A points to B, B does not necessarily point to A. Example: check Twitter, X, follow, check dependency, check money transfer, check web page link. Weighted graph. Edges have weights. A, 5, B, 2, C. Weight can mean distance, cost, time, risk score, latency, strength of relationship. Unweighted graph. All edges have equal cost. A, B, C. Used when only connection matters. Distance is number of edges. Shortest path means fewest steps. Graph representation. Graphs are commonly represented using adjacency list, adjacency matrix, edge list. Step 1. Adjacency list. Adjacency list stores neighbors for each node. Example: A, B, C, B, A, D, D, E. Java. Map string list string graph equals new hash map. Graph.put A, list of B, C. Graph.put B, list of A, D. Graph.put C, list of A. Graph.put D. Best for: yes. Sparse graphs? Yes. Most interview problems? Yes. Real-world relationship data. Time to iterate neighbors. O, number of neighbors. Step 2, adjacency matrix. Adjacency matrix uses a 2D array. Example: A, B, C, A, 0, 1, 1, B, 1, 0, 0, C, 1, 0, 0. Java. int-ll graph equals 0, 1, 1, 1, 0, 0, 1, 0, 0. Best for: dense graphs, quick edge lookup, small graphs. Edge lookup. O1. Memory. OV squared. Step 3. Edge list. Edge list stores all edges. Example: A means B, A means C, B means D. Java. Class edge, string from, string to. Edge string from, string to. This from equals from. This to equals. List edge edges equals list of new edge AB, new edge AC, new edge BD. Best for: algorithms like Kruskal, importing, exporting graph data, database relationship records. Step 4. BFS, breadth first search. BFS means visit graph level by level. Uses queue. Start, visit neighbors of neighbors. Example: A, K, B, K, D, BFS order. A, B, C, D, BFS Java example. Public void BFS, string start, map string list string graph. Queue of string queue equals new linked list set. Set of string visited equals new hash set. Queue.add start. Visited.add start. While not queue is empty. String current equals queue poll. System out println current. 4. String neighbor dot getter default current list dot of. If not visited dot contains neighbor. Visited dot add neighbor. Queue dot add neighbor. Use BFS for: shortest path in unweighted graph. Shortest path in unweighted graph. Nearest connection. Minimum number of steps. Social network distance. Step 5. DFS. Depth first search. DFS means go deep first before backtracking. Uses recursion or stack. Start, go deep, backtrack, explore next path. Example: A, B, R, C. DFS order. A, B, D, C. DFS Java example. Public void DFS, string node, map string, list string graph, set string visited. If visited contains node, return. Visited.add node. System.out.println node. 4. String neighbor, graph.get or default, node, list of. DFS neighbor, graph visited. Call. DFS, A, graph, new hash set. Use DFS for: connected components, cycle detection, path finding, graph traversal, topological sort, backtracking problems. BFS versus DFS. Feature: BFS, DFS. Data structure: queue, stack, recursion, traversal, level by level, deep first, best for shortest path unweighted, explore all paths. Memory, can be larger, can be smaller. Common use: minimum steps, cycle path traversal. Simple rule: use BSF when you need shortest number of steps. Use DFS when you need to explore structure deeply. Step 6. Connected components. Connected component means a group of nodes connected together. Example: Component 1, A, B, and C. Component 2, D, E. Problem: count how many separate groups exist. Java. Public int count components. Map integer, list integer, graph. Set integer, visited, equals new hash set. Int components equals 0. For integer node, graph.keyset. If visited.contains node, components plus DFS node, graph visited. Return components. End. Private void DFS. Integer node. Map integer, list integer, graph. Set integer visited. If visited contains node, return visited.add node. 4. Integer neighbor. Graph.getterDefault node. List of DFS neighbor, graph visited. Use cases: hashtag friend groups, hashtag network clusters, hashtag disconnected services, hashtag island problems. Step 7. Cycle detection in undirected graph. Cycle means you can start at one node and return to it. Example: A, B, B, C, D. Java. Public Boolean has cycle undirected, int node, int parent, map integer, list integer, graph, set integer visited. Visited, add node. For int neighbor is graph.getOrDefault node, list of. If not visited contains neighbor. If has cycle undirected neighbor node graph visited, return true. Else if neighbor is not parent, return true. Return false. Important: in undirected graph, ignore the edge back to parent. Step 8. Cycle detection in directed graph. Directed cycle example: A means B means C, up, down. Use two sets. Currently visiting, visited. Java. Public Boolean has cycle directed. String node, map string, list string, graph. Set string visiting, set string visited. If visiting.contains node, return true. If visited.contains node, return false. Visiting.add node. For string neighbor, graph.getOrDefault node list of. If has cycle directed neighbor, graph, visiting, visited, return true. Visiting, remove node. Visited, add node. Return false. Use cases: course prerequisites, package dependencies, build pipeline dependencies, workflow validation. Step 9. Topological sort. Topological sort is ordering nodes so dependencies come before dependents. Example: database means backend, means frontend. Valid order: database, backend, frontend. Used for check course schedule, check build order, check deployment order, check dependency resolution, check workflow execution. Only works for directed acyclic graph, also called DAG topological sort. Java example: public list string, topological sort, map string, list string, graph. Set string visited equals new hash set. Stack string stack equals new stack. For string node, graph.keyset. If not visited contains node. DFS topo node, graph, visited, stack. List string result equals new array list. While if stack is empty, result add stack pop. Return result. Private void DFS topo, string node, map string, list string, graph, set string visited, stack string stack. Visited.add node. For if neighbor, getOrDefault node, list of. If visited contains neighbor, DFS topo neighbor, graph, visited, stack. Stack push node. Step 10. Shortest path in unweighted graph. Use BFS. Problem: find shortest number of steps from A to D. Java. Public int, shortest path unweighted. String start, string target, map string, list string, graph. Q_string equals new linked list. Map string integer distance equals new hash map. Set string visited equals new hash set. Q.add start. Visited.add start. Distance.put start 0. While Q.is empty. String current equals Q_pol. If current equals target, return distance.get current. For string neighbor, graph.get or default current list of. If not visited contains neighbor, visited add neighbor. Distance put neighbor, distance get current +1. Q add neighbor, return -1. Use cases. Capital M minimum clicks, shortest friend connection, shortest route by number of stops, minimum transformation steps. Step 11, Dijkstra algorithm. Dijkstra is used for shortest path in weighted graph with non-negative weights. Example: A5B, A2C, C1B. Shortest path from A to B. A means C means B equals 3. Not. A means B equals 5. Dijkstra Java example class. Weighted edge, int2, int weight. Weighted edge, int2, int weight. This.2 equals 2. This.weight equals weight. Public, int Dijkstra, int start. Map integer list weighted edge, graph, int node count. Int distance equals new int node count. Arrays.fill, distance, integer max value. Distance start equal 0. Priority queue int IP. PQ equals new priority queue comparator.comparing int AA1. PQ.add new int start 0. While PQ is empty. Int current equals PQ.poll. Int node equals current 0. Int current distance equals current 1. If current distance equals distance node. Continue. For weighted edge, graph.get or default node, list of edge. Int new distance equals current distance plus edge.weight. If new distance equals distance edge 2. Distance edge 2 equals new distance. PQ add new integer edge 2, new distance. Return distance. Use cases. Route planning, network latency, cost optimization, delivery systems. Step 12. Union find, disjoint set. Union find is used to manage connected groups. Useful for connected components, cycle detection, Kruskal algorithm, grouping accounts, network connectivity. Operations. Operation meaning find group root, union merge two groups, connected check same group, union find Java example, public class union find, private final int parent, private final int rank, public union find int size, parent equals new int size, rank equals new int size. For int I equals 0, I not size, I plus, parent I equals I. Public int find, int x. If parent x equals x, parent x equals find parent x. Return parent x. Public boolean union, int a, int b. Int root a equals find a. Int root b equals find b. If root a equals root b, return false. If rank root a greater than rank root b, parent root a equals root b. Else if rank root b greater than rank root b, parent root b equals root a. Return true. In step 13, graph problems and interviews. Common graph patterns. Pattern example, BFS, shortest path in unweighted graph. DFS, explore all nodes, connected components, number of islands, cycle detection, course schedule, topological sort, task ordering, union find, group merging, Dijkstra, weighted shortest path, backtracking, all paths, matrix graph, grid traversal. Step 14, matrix as graph. Many grid problems are graph problems. Example, 1 1 0 0 1 0 1 0 1. Each cell is a node. Neighbors. Up, down, left, right. Used for check number of islands, Check shortest path in grid. Check rotten oranges. Check maze problems. Check flood fill. Matrix DFS example. Public int num islands, char grid. Int rows equals grid.length. Int cols equals grid0.length. Int count equals 0. For int row equals 0, row less than rows row. For int col equals 0, col less than cols. If grid row col equals 1, count plus DFS grid row col. Return count. Private void DFS char grid int row int col. If row is 0, or row is grid.length, or col is 0, or col is grid0.length, or grid row col is not equal to 1. Grid row col equals 0. DFS grid row plus 1 col. DFS grid row minus 1 col. DFS grid row col plus 1. DFS grid row col minus 1. Step 15. Graph use case in backend systems microservice dependency graph. Example. API gateway means order service. Order service means payment service. Order service means inventory service. Payment service means fraud service. Use graph algorithms for. Done. Find affected services. Detect circular dependencies. Identify critical services. Map service ownership. Visualize architecture. Question. If payment service fails, what services are affected? Graph traversal can answer this. Step 16. Graph use case in authorization. Permission graph. Admin means manager, means user, means read only. Use graph traversal to collect inherited permissions, detect permission cycles, validate role hierarchy, calculate effective access. Important. Always detect cycles in permission graphs. Step 17. Graph use case and recommendations. Product recommendation graph. User means viewed, means product user, means purchased, means product. Product means belongs to, means category. Product means similar to, means product. Use graph traversal to find. Check similar products. Check users with similar behavior. Check related categories. Check recommendation candidates. Step 18. Graph use case in dependency resolution. Example. Module A depends on Module B. Module B depends on Module C. Use topological sort to determine build order. Module C, Module B, Module A. If cycle exists, build cannot be completed safely. Step 19. Graph database basics. Graph databases store relationships directly. Examples. Neo4j, Amazon Neptune, Janus Graph, ArangoDB. Graph database model. User follows user, user purchased product, product belongs to category. Use graph database when click relationships are first class. Traversals are common. Many joins become complex. Recommendation, fraud, social graph is central. Step 20. Graphs versus relational databases. Feature relational DB, graph DB. Data model, tables, nodes and relationships, relationship handling, joins, edges. Best for transactions, connected data. Query style, SQL, graph traversal. Example, PostgreSQL, Neo4j. Simple rule. Use relational DB for structured transactional data. Use graph DB when relationship traversal is the core problem. Step 21. Graph learning roadmap, beginner level. Learn. Check nodes, edges, directed graph, undirected graph, weighted graph, adjacency list, BFS, DFS. Build. Simple social network graph, intermediate level. Learn. Connected components. Cycle detection. Matrix graph problems. Shortest path unweighted. Topological sort. Union find. Build. Course prerequisite, resolver advanced level. Learn. Check. Dijkstra, Bellman-Ford basics, minimum spanning tree. Graph database basics. Recommendation graph. Fraud detection graph. Microservice dependency graph. Build. Graph-based recommendation or dependency analysis system, 30-day learning plan, week 1. Graph basics. Learn. Graph vocabulary. Graph types. Adjacency list. Adjacency matrix. Edge list. BFS. DFS. Practice. Implement BFS and DFS in Java. Week 2. Core interview problems. Learn. Connected components. Number of islands. Cycle detection. Shortest path in unweighted graph. Grid traversal. Practice. Solve 10 BFS/DFS problems. Week 3. Dependency and ordering problems. Learn. Directed graph. DAG. Topological sort. Course schedule. Build order. Dependency cycle detection. Practice. Build course prerequisite validator. Week 4. Advanced graph algorithms. Learn. Dijkstra. Union find. Minimum spanning tree basics. Graph use cases. Graph database basics. Practice. Build service dependency analyzer. Graph roadmap chart. Common graph interview questions easy. Find if path exists. Count connected components. Flood fill. Number of islands. Clone graph. Medium. Course schedule. Rotting oranges. Pacific Atlantic water flow graph. Valid tree. Number of provinces. Shortest path in binary matrix. Evaluate division. Advanced network delay time. Flights within K stops. Reconstruct itinerary. Critical connections. Minimum spanning tree. Word ladder. Alien dictionary. Interview question 1. What is a graph? A graph is a data structure made of nodes and edges. Nodes represent entities. Edges represent relationships. Example. User means follows means user interview question 2. BFS versus DFS. BFS visits nodes level by level using a queue. DFS visits nodes deeply using recursion or stack. Use BFS for shortest path in unweighted graph. Use DFS for exploring all paths, components, and cycle detection. Interview question 3. What is a directed graph? A directed graph has edges with direction. Example. A means B. Meaning. A points to B. B does not automatically point to A. Interview question 4. What is a weighted graph? A weighted graph has cost value on edges. Example. A, 10, B. Weight can represent. Check, distance. Check, cost. Check, latency. Check, time. Interview question 5. What is topological sort? Topological sort orders nodes so dependencies come before dependents. It works only on directed acyclic graphs. Use cases. Course prerequisites. Build order. Deployment order. Workflow execution. Interview question 6. How do you detect cycle in a directed graph? Use DFS with, visiting set, visited set. If a node is seen again in the visiting set, there is a cycle. Interview question 7. What is union find? Union find is a data structure used to manage disjoint sets. It supports find union, connected check. Use for connected components, cycle detection, grouping problems. Interview question 8. When do you use Dijkstra? Use Dijkstra for shortest path in a weighted graph with non-negative edge weights. Common beginner mistakes. 1. Forgetting visited set. Bad. DFS neighbor. Without visited set. Problem. Cycles can cause infinite recursion. Better. If not visited dot contains neighbor. DFS neighbor. 2. Using DFS when BFS is better. If the problem asks minimum number of steps. Usually use BFS 3, confusing directed and undirected graphs. Directed, A means B. Undirected, A and B. This changes traversal and cycle detection. 4. Not handling disconnected graphs. Bad. Start DFS from one node only. Better. Loop through all nodes and start DFS if unvisited. 5. Wrong matrix boundary conditions. Always check. Row less than 0. Row equals rows. Col equals cols. 6. Mutating input without knowing. In matrix DFS, grid row col equals 0. This is fine sometimes, but if input must remain unchanged, use a visited matrix. Best practices. Check represent graph clearly. Check use adjacency list for most problems. Check always think about visited set. Check identify directed versus undirected. Check identify weighted versus unweighted. Check use BFS for shortest unweighted path. Check use DFS for traversal and cycle detection. Check use topological sort for dependencies. Check use union find for grouping and connectivity. Test disconnected graphs. Test cycles. Test single node graph. Test empty graph. Draw the graph before coding. Explain time and space complexity. Time complexity cheat sheet. Algorithm time complexity. Space complexity. BFS. OV plus E. OV. DFS. OV plus E. Connected components. OV plus E. OV. Cycle detection. OV. Topological sort. OV plus E. OV. Dijkstra. O plus V log V. OV plus E. Union find. Almost 1 per operation. Where V equals vertices, nodes. E equals edges, connections. Real-world project idea. Project. Microservice dependency analyzer. Build a system that tracks dependencies between services. Example. Order service calls payment service. Payment service calls fraud service. Order service calls inventory service. Features. Add service. Add dependency. List dependencies. Detect cycles. Find affected services. Topological deployment order. Visualize graph. Expose REST APIs. Architecture. React, Angular, front-end. Spring Boot API. Graph service. PostgreSQL, Neo4j. Endpoints. Post API services. Post API dependencies. Get API services ID dependencies. Get API services ID affected. Get API deployment order. Get API cycles. Graph algorithms used. Check. DFS, BFS, cycle detection. Final summary. Graphs are one of the most important data structures for software engineers. Important concepts include nodes, edges, directed graphs, undirected graphs, weighted graphs, adjacency list, BFS, DFS, connected components, cycle detection, topological sort, shortest path, Dijkstra, union find, matrix graph problems, graph databases, real-world graph systems. Software engineers use graphs for interviews, backend systems, dependency analysis, recommendation systems, fraud detection, permission hierarchies, social networks, cloud infrastructure maps. Key idea. Graphs help software engineers model and solve problems where relationships, paths, dependencies, and connections are the main focus.